Welcome back, everyone, for our second session. And our next speaker will be introducing their methodology on detecting missing relationships from biomedical ontology and terminologies. Rashmie, are you ready?
Yes.
Okay, go ahead.
All right. So thank you very much for the introduction. So our paper is based on a quality assurance work that was performed on two ontologies, SNOMED CT and thesaurus, to identify missing user relations. So these are my co-authors, Drs. Fengbo Zhang, Jie Shi, Samden Latu, and Li Cui. So this is a brief outline of my presentation. So I will first briefly introduce you to thesaurus and SNOMED CT and discuss why ontology quality assurance is important, and introduce you to non-lattice subgraphs, which are graph fragments where we look for these missing user relations, and we'll discuss the methods that were undertaken in detail. Show you some results and the evaluation performed as well. So SNOMED CT is the largest clinical terminology in the world. So it contains the current version actually contains more than 350,000 active concepts. Contains concepts that provide codes, terms, synonyms, and definitions to be used in clinical documentation and reporting. It's widely used in EHR systems as well, and its concepts are organized in 19 different subhierarchies, like clinical findings, which itself contains over 100,000 concepts, body structure, procedure, and so on. thesaurus is widely used in cancer-related research, including containing concepts related to cancer-related diseases, findings and abnormalities, anatomy, drugs and chemicals, genes and gene products, and so on. And it's a rather large ontology as well. It contains over 180,000 concepts in its latest version. Each concept of thesaurus has rich resources with a unique code, a preferred name, different abbreviations, synonyms, and definitions. It is hierarchically organized in 19 domains as well. So biomedical ontologies are regularly updated to reflect the state of the art. So during this process, new concepts are introduced, existing concepts are enriched, maybe with new relations or annotations. So during this process, errors may be introduced as well, even though there are like internal quality checking processes of application of reasoners, which ensures the logical consistency of an ontology. And also some ontology curators leverage the user reporting of bugs through functionalities like GitHub issue trackers, so that users could report back the issues that they find, so that the ontologies could improve. But still, there exist errors. So due to that, ontology quality assurance has become like an essential part in terminological management. This is very important because errors in an ontology could actually propagate to downstream applications that use these ontologies as a knowledge source and make them less accurate as well. For instance, I have here a missing user relation that we have found in our previous work, one of our previous works in the thesaurus. So in an application that used this ontology, for instance, for a clinical cohort identification application, if you're getting a clinical cohort with patients having gallbladder papillary neoplasm, then due to this missing relation, missing user relation, the patients with gallbladder papillary adenoma will be missed from that cohort. So Ontology collision is very difficult to perform manually because manual review it takes time and also very labor intensive as well. And because modern biomedical ontologies are very large in size and very complex in their structure, it's very impractical and not sustainable to put manual effort into completely auditing them. So there's a need to actually develop automated approaches that identify and fix these different types of issues. So our work is actually based on non-lattice subgraph, which we have introduced in previous work, and we have leveraged in some other works as well to identify and fix different kinds of issues in different kinds of ontologies. So we look for these missing ether in these graph fragments that we know that we name as non-lattice subgraphs. So the whole idea is that being a lattice is considered as a desirable structural property for a well-formed ontology. And the definition of a lattice is a directed acyclic graph where any two nodes have a unique maximal common descendant and a unique minimal common ancestor. And pairs of concepts that violates this lattice property is known as non-lattice pairs. And a non-lattice subgraph is extracted from a non-lattice pair through a reverse computation by obtaining its obtaining the minimal common ancestors of the maximal common descendants of the non-lattice pair. So our method, as I mentioned previously, is an approach to identify missing ether relation. So ether relation is a very important relation in an ontology, which denotes the hierarchical arrangement of concepts. So these are the major steps of our approach. First, we identify candidate concept pairs that we look for ether relations in. And then there are two aspects of subsumption checking: logical definition-based subsumption checking and lexical-based subsumption checking. And the resultant set of potential missing ether relations are further refined by removing redundant missing ether relations. So a pair of concepts is considered as a candidate pair that we look for ether relations in if they are in a non-lattice subgraph, and if they're not hierarchically related, meaning that they don't have an ether relation in between. For instance, this is a non-lattice subgraph in SNOMED CT. And for instance, this one, concept number 6 and 7, they would form a candidate pair as well because they are not hierarchically related. And 7 and 8 would form another candidate pair. So likewise, this non-lattice subgraph have many such candidate pairs. However, 6 and 1 would not form a candidate pair because they have an ether relation in between. So this is a non-lattice subgraph in the National Cancer Institute thesaurus. And again, these 2, 4, and 6 would form a candidate pair. 2 and 1 would form another candidate pair. Likewise, 7 and 8 would form a candidate pair as well, but 8 and 2 would not because they have an ether relation between them. So each SNOMED CT concept is also NCT source concept is logically defined with attribute value pairs, and attribute value pairs are actually grouped to avoid ambiguity in how they apply. For instance, these are the logical definitions of the SNOMED CT concept: malignant neoplasm of peripheral nerve of abdomen. So it has one ether relation and 2 attribute value pairs. So this finding set is an attribute, and structure of peripheral nerve of abdomen its value, and likewise this is another attribute value pair, and the 2 of them have been grouped together. So this is a screenshot from the NCT thesaurus browser where it's the definitions of this particular NCT thesaurus concept. So it has 2 ether relations and these attribute relations. And in both ontologies, some concepts may have complete logical definitions where we name them as fully defined, and some concepts may not, which we say that are primitive. So to perform logical definition-based subsumption checking, what we do is we compare these attribute groups of one concept with another. And we say that if for each relation group of one concept, if there exists a corresponding relation group in concept, the other concept that is more specific than one concept can be logically subsumed based on logical definitions. It can be logically subsumed. So, for instance, for this particular concept, if you consider the first group, I mean, they're pretty much the same. But in the second one, they're not the same, but they have the same relation ether. And the value actually, neoplasm of abdomen is actually a parent of this malignant neoplasm of abdomen. So in that case, we say that this attribute, this attribute value pair is more specific than this one. Likewise, in this attribute group, this one has the same relation, associated morphology, while neoplasm is actually an ancestor of this malignant neoplasm of primary, secondary, or uncertain origin, which makes this attribute value pair more specific than this one. These two are the same as well, the final two attribute value pairs. So this makes this particular, the second concept actually more general than the first concept based on their logical definitions. And then we also perform this lexical-based subsumption checking, where we first construct these lexical feature sets for each concept based on their concept names and their ancestor concept names. And we actually do it using three sources. The first is based on dependency parsing, the dependency pairs identified through dependency parsing. We perform a dependency parsing of concept names and identify two kinds of dependencies, object of preposition and direct object. And then we also aggregate based on phrases accessing concept names. And finally, single words that were not part of dependency pairs. So this would form the lexical feature set of a particular concept. And then we enriched this lexical feature set of the concept with all the lexical feature sets of its ancestors to sort of obtain a broader view of the semantics of the concept. So this is an example of lexical feature set for the concept, SNOMED CT concept, malignant neoplasm of peripheral nerve of abdomen. So you have these are the initial lexical feature set for the extracted by the concept itself. So you have of nerve of abdomen, which were obtained through dependency parsing, and then malignant neoplasm, peripheral nerve, which were noun chunks or based on phrases, and malignant neoplasm and peripheral, which was words, single words. And then you have the enriched set of lexical features containing all such lexical features of its ancestors. So given a candidate pair, X and Y, we suggest a potential missing is a relation, X is a Y, if X is more specific than Y in terms of logical definitions. And then if the enriched set of lexical definition of X is actually a superset of Y. So if both these two conditions are satisfied, then we suggest potential missing is a relation, X is a Y. So this is an example of such missing is a relation, rather two missing is potential missing is relations that were found in a non-lattice subgraph of SNOMED CT in SNOMED CT. So you have the non-lattice subgraph on the left, and two dashed lines in red are the potential missing Isa relations identified. So one goes from malignant neoplasm of peripheral nerve of abdomen to neoplasm of peripheral nerve of abdomen, and same parent but a different child here. Benign ganglioneuroma of abdomen is a neoplasm of peripheral nerves of abdomen. So yeah, so these potential missing Isa relations may make some of the existing Isa relations redundant. For instance, you had an Isa relation initially between 6 and 1, but that is implied through 6 and 8, the new Isa relation, as well as 6, 8 and 1, the existing Isa. So some of the Isa relations have been removed because they are implied by existing Isa and potential missing Isa. So this is an example of from NCH saurus. So you have the original non-lattice subgraph on the left, and the missing Isa relation denoted by this dashed line, dashed arrow in red. So again, existing Isa between 4 and 3 and 4 and 2 have been removed because that's implied through this part, as well as this 4, 6 and 3 part. So some of the potential missing Isa relations suggested by our method could actually be implied through other potential missing Isa relations and existing Isa relations. So in that case, it does not make sense for us to suggest those missing Isa relations. So they will be removed from the set of final set of Isa relations suggested by our method. So for instance, if our method suggests two Isa relations, X is a Y and X is a Z, and if there's exists an Isa relation, Y is a Z in the ontology, then X is a Z is actually implied by X is a Y and Y is a Z. So because of that, we do not suggest X is a Z because that can be inferred. So in terms of the results, SNOMED CT had around 350,000 concepts, and NCH saurus had around 180,000 concepts. And these are the number of non-lattice subgraphs: 234,000 for SNOMED CT and 14,000 for NCH saurus. And these are the number of non-redundant potential missing Isa identified in SNOMED CT: 982 for SNOMED CT and 102 for NCH saurus. So we leverage the support of domain experts to evaluate some of these potential missing Isa that were identified by our method. So we picked a random sample of 150 potential missing Isa relations from SNOMED CT from these two subhierarchies, clinical finding and procedure, and which were reviewed. And it was seen that 118 were valid. So 78.67% were valid cases. And then we also evaluated 20 potential missing Isa relations from NCRD's drug, food, chemical, or biomedical materials hierarchy, and 17 of them were deemed as valid missing Isa cases. So in conclusion, we introduced this automated approach that is able to identify and fix missing Isa relations between candidate concept pairs in null subgraphs. So the approach sort of combined logical definition based subsumption checking and lexical based subsumption checking. And based on the review, it was seen that the method is effective in accurately identifying missing Isa relations. And in the future, we would like to further normalize these lexical attributes by maybe performing lemmatization and synonym replacement. And also, so while we suggested these missing Isa relations, the fix might not be directly adding them to respective ontologies. Fix may involve different complicated steps like changing the logical definitions of concepts so that the missing Isa relation can be inferred. or maybe even there might be intermediate concepts among these two concept pairs that we suggested missing is relations between. So the fixes might be complex, and we would like to investigate further into root causes that cause these missing is relations. And also, large language models are very hot right now, and we would like to see whether they could be leveraged to predict missing is relations, which would be a nice contribution as well. So I would like to thank my co-authors and the funding support by NSF and NIH. And yeah, thank you.
Thanks, Rashmie. Do we have any questions from the audience?
Yeah, I just have one quick question. I think it's a very good presentation, and you also mentioned in your future direction, just say improve the larger axons, just say whether it could be inferred to the to fill in that missing is a relation. So I just wondering, because I haven't worked, I just using the SNOMED some terms, but not really work on their, using their ontology. So the SNOMED, the version you're using, is after running the reasoner or not?
It's the inferred version. So it's after running the reasoner. So these missing is relations have not been captured by the reasoner, because some of these concepts are actually primitive. So their logical definitions are not complete. So the reasoner actually does not identify like missing is relations among concepts that are primitive.
Okay, yeah, that sounds makes sense. Also, is the SNOMED contain some equivalent logic axons when they define the concept? Because I have no idea, so I just care about that.
You mean equivalence of?
Yeah, logic axon that is really helpful to infer the is-a relation.
Yeah. So it does. Yeah. So it has like very rich logical definitions. So if the concept is fully defined, which means it can be uniquely identified through its logical definitions, so it would have like an equivalence relation between the concept and their logical definitions.
So they do have a lot of defined using the equivalent logic.
Yeah, equivalence in terms of the definition as well to the concept. Yeah. There are quite a bit of fully defined concepts that has that, but there are a lot of primitive concepts with incomplete definitions as well. Yeah.
Okay, thanks. Because of the issue you mentioned that we also found, in the OBO, because I am the developer of OBO foundry ontology, we using that equivalence things and then try to catch that missing is-er, and also the remove redundant is-er, doing that inference process. So it's kind of some of that missing in the SNOMED, right?
Very interesting.
Yeah, thank you. It's really good work.
Thanks.
Yeah, Rashmie, I also have a question for you. So you mentioned the large language models can play a role here. I'm just curious if you guys have done any work on that direction, and maybe you can elaborate a little bit. Because I think this is really emerging direction basically.
So we haven't actually done much experiments here. We've tried to see whether like I'm providing these models with just the two concepts and asking to predict is a relation without doing any like prompt tuning or anything.
Right.
Hasn't performed that well. So I would guess maybe we would have to like experiment more in terms of how to sort of train it using existing ISA relation to see how effective it would be in terms of accurately predicting missing ISA relation. So we haven't done much in this aspect yet, but that's very interesting.
Yeah. And other than ISA relations, Do you guys also plan to work on maybe other important relationships?
Yeah, we have worked on like other types of relations, maybe not in SNOMED CT, but in gene ontology, we have in thesaurus, we've audited part of relations, and in gene ontology, we've actually audited regulation of and different kinds of relations as well. So yeah, we've done that, and we are expecting to apply such approaches for SNOMED CT relations too.
Amazing. Thank you.